I didn't see those notes behind mine.
All right, we are continuing to talk about volumes, and today we're just going to do a bunch of examples. Now, I discovered, mainly through our differential equations class and some resources that are available through its textbook, that there's a site where I can do some visual demonstrations for you right here in class to maybe help you get a little bit better mental picture of what it is we're trying to do. I've tried to draw these things as well as I can three-dimensionally, but it helps to be able to see something moving around in front of you. I will go ahead and broadcast to your screen so you see what I see. So on my desktop actually here, I've gone to a site called demonstrations.wolfram.com. In fact, on all these computers in here, I've installed a special piece of software called the Wolfram CDF player. It's kind of like, you know what PDFs are, the portable document format. You have to have some kind of player that will show those. It's now built into all the browsers, but Wolfram, same guy that does Wolfram Alpha, also same guy that has written Mathematica, the software, mathematical software that does a lot like what Maple does. He developed what he calls a computational data format, which allows for things like what you see on the screen right here to be put into documents. The player is actually free. If you go to demonstrations.wolfram.com and you do a search there, in fact, all I did was a search for solids of revolution, and it took me to this page right here. So I just went and searched for solid of revolution, and this is an example. If you don't have that player installed, you can download it for free to your own computer, or you can come into a lab like this one and take a look at it. If you just want to go back and look at some of these, none of these will actually, I don't think, as far as I can predict at this point, will be required as part of your homework to be able to see these things outside of class. But, I mean, it helps you to get a better understanding of what's going on in here. So here's the idea, like what we talked about last time. If you've got two curves, and what we're going to do is we're not going to find the area between the curves. That was 6.1. We're going to take that area, and we're going to revolve it around the x-axis. Okay? So we're going to take that thing and move it in this circle around the x-axis. So it's going to come out towards you on the screen and go all the way back around away from you. And so I've tried to describe that to you with my crude three-dimensional drawings, but it's easier to see if I just drag this, that this is what I was talking about doing. Okay? And as you rotate this thing around, you can see what I'm actually doing is just dragging that all the way around to create a volume now that is bounded on the outside by the f of x and on the inside by the g of x. Okay? Now the question is, what's the volume of that piece? And that's what we did. We weren't quite to an example with two curves, but we did an example without a hole in the middle. We'll look at different ones today that have holes in the middle and try to draw them as best we can. But the real trick, all that we need to do a volume of revolution is to look at a cross-section and find the area formula for the cross-section based on what x I'm at, and then integrate that over the range of all possible cross-sections. Okay? Find what the cross-section looks like as a function of x. Now, when you're looking at this guy, notice just at the end you can see this. The cross-section is these two concentric circles, an annulus, right? A circle with a hole cut out of the middle of it. And the area of that is the area of the outside minus the area of the inside. So it's pi f of x squared minus pi g of x squared. And if you do that, now you just integrate over that. So you basically have a formula as long as you set the problem up correctly. And that's what we're going to do several examples of today. All right, so back to our notes. We made it to an example. By the way, those are the two formulas for the areas that we're going to integrate. So remember, the steps to this are to draw the figure, find out what your radius is. If there's two radii, an outer and an inner one, you use this second formula. If there's just one radius, if it's just one circle, then you use this formula. And then again, you integrate, which is what I've got up here, the area from A to B and the area from C to D, depending on which axis you're revolving around. Because we can revolve around the x-axis, we can revolve around the y-axis. Okay? So we did this one. We rotated 1 over x from 1 to 4. And we were just about to get started on this one. So I've already drawn the picture for us last time. I want to get rid of this thing if I can. There. Okay, so what I did last time was we started with this curve, x equals 2 square roots of y, and I graphed it. And there's you can use whatever graphing tools you have available to you, Wolfram Alpha, your graphing calculator, or just start plotting some points. I graphed x equals 0 and y equals 9 first, and then looked at different values I could plug in for y to see what I got for x, and that's where I came up with the blue curve, and now got that region. And it says I want to revolve that around the y-axis. So since I'm revolving around the y-axis, the cross sections I'm going to take now are going to be horizontal. That is, I'm going to select some y here and slice through that solid and look at what the cross section looks like, right? Which is going to be that circle right there. You don't always have to draw all of this. Once you kind of start to get the hang of this, you recognize that you know exactly what shape it is. It's always going to be a circle when you're doing revolved solids. But now you got to figure out what's that radius. What's the distance from the axis or the center here out to that point? And that comes straight from your function almost always. Okay? It's 2 square roots of y. Because at a given y, the distance to that curve is 2 square roots of y. Okay? So I'm going to say then that the area is pi times 2 square roots of y squared. Or, simplify that. 4 pi y, right? So now, I'm going to integrate that. 4 pi y, right? That's the area of the cross section, pi r squared, dy. And what are all the possible y's then, as I've chosen one y right here? What's the range of y's that it goes from? 0 to 9. Now you've set up your integral. The rest is just Cal 1. Okay, so what's the integral of 4 pi y? The constant sticks around. Y squared over 2, so I could actually just write that as 2 pi y squared. Right, or I'm going to do it the long way. 4 pi y squared over 2 becomes 2 pi y squared. And then plug in 0 to 9. So 2 pi 9 squared minus 2 pi 0 squared. Uh, 81 times 2, 162 pi, minus 0, so the volume is 162 pi. Okay? Does the procedure make sense? Okay, again, depending on which axis you're going to rotate it around, you're going to choose either a y or choose an x, and then look at the cross section, find the area of the cross section, integrate that over the interval of all possible cross sections. That's it. Okay, it's not always as easy as just eyeballing it and plugging in the function. You've got to draw the figure first because, as you'll see in my next 3 examples, it can change based on where you're revolving and what functions are involved. Okay, so the next 3 examples, I think, all involve the same region. I'm going to be revolving the region around different lines and see what shapes I get out of it. Okay, so first of all, let's find what region R we're talking about. So in this example, number 3, 4, and 5, I've got a region enclosed by the curve y equals x and y equals x squared. So first thing you do is just graph both of those on the same graph. And I think most of you should be able to do that even from scratch without needing a calculator. Just think it through. What's the curve look like for y equals x? Straight line, 45-degree angle, right? Slope 1. Okay, and then what's y equals x squared look like? It's a parabola, right? Now, just to emphasize where these things are going to cross, I know that a parabola starts out going horizontal, then turns up. When I go over 1, the parabola ends up at a height 1, right? So when you graph those on top of each other, and it says the region enclosed by the curve y equals x and y equals x squared, where's the region that's enclosed? It's that little sliver. Okay? So in fact, what I'm going to do, and I don't know how well this will work. I'm going to draw just those pieces. So I just erased everything I did, but you guys can either erase or get back to where I was. I'm going to, for color's sake, I'm just going to try to get this as straight as possible in blue. And then there's a parabola going like that. Okay? Actually, I want to get that even better. I don't like that. I'm going to have to be using this a lot. What if I zoom way in? Ooh, look at there. Okay, so straight line. Much better. Okay. So there's my region R. Now in the first example, example 3, what am I going to revolve this thing around? All right, so I'm going to be going, where'd my pen go? Right this way. So whenever you revolve around the x-axis, then you basically draw a mirror image of that curve on the other side. And then I like to connect them with these ovals to make it look 3D. Okay? I'm going to switch my colors back to red. So there's the idea. It's going to kind of have this cone on the outside and a bend on the inside as you go down towards that point, right? The question is, what's the volume of the actual piece that gets revolved around here, right? So here's now where you've got to think what the outer radius and the inner radius are going to look like. Okay? So the cross section is a washer. Okay? What's the inner? Actually, I like to start with the outer. What's the outer radius? It's x. Because it's the outside function. That makes sense to you, right? And the inside? X squared. Okay, so now going back up, I'm going to leave this screen for just a second. Remember that if you've got a washer, the area is pi outer radius squared minus pi inner radius squared. Okay? So the area for a given x, I'm on the x-axis here, is pi times x squared minus pi times x squared squared. Outer radius, inner radius. Or pi x squared minus pi x to the fourth. So your integral for the volume is going to be the integral of pi x squared minus pi x to the fourth dx over what range? 0 to 1. Again, notice in this case, they didn't give us 0 to 1 in the problem anywhere. We have to figure that out from where these two curves intersect, right? So you can look at the graph to do that. I mean, if your graphing tool allows you to figure out where those two things intersect, then you can use the graph to do that. Sometimes that's not immediately obvious. Sometimes you'll look at the graph and it's like 6.2814 or something, right? And you're like, should I go to the decimal place or is there an exact value? The way that you figure out where they intersect, set them equal to each other. Find intersections by f of x equal g of x. In our case, x equals x squared, right? Which would be x squared minus x equals 0, which you can factor and get x equals 0 and x equals 1. That's where my limits technically come from, is the fact that that's where those two curves intersect. Okay? And then the rest is Cal 1. The easy part of Cal 1. Not the proofs of the theorems, but the mechanical calculations. Pi x cubed over 3 minus from 0 to 1. Which will be 1/3 minus 1/5 minus 0 minus 0, right? Oh, pi over 3, pi over 5. That's pi's. I don't know why I did that. You can always tell when I do something crazy. It's at least 4 eyebrow or foreheads that wrinkle up real bad in here. What are you talking about? What? And what's pi over 3 minus pi over 5? 1/3 minus 1/5.
So you get 15, so 5/15, so it's 3/15. So 2/15, pi 2/15. 2 pi 15.
Right, 5/15 minus 3/15 gives us 2 pi 15. Or 2/15 times, and then the pi, I just add back in. Okay, so next question is similar, but it says take the same region and rotate it about the line y equals 2. Not even the y-axis, but now some other line. Okay? Has everybody got example 3? Can I move on? Okay, I'm scrolling down. Okay, so we got to draw the shape again, but now we got to draw this on an axis big enough so that I can rotate something around y equals 2. So first of all, where is y equals 2? It's right here, and as a line, what does the graph of the line y equals 2 look like? Horizontal, right? Everything that has a height of 2. There's your y equals 2. Now remember, my shape for my curve is down here. Now what I want to do is I want to take that shape and revolve it at every point around y equals 2. Okay, so now instead of being that kind of cone with the bevel inside, it's going to be this dome-looking thing on the outside with a big hole in the middle, right? Because again, the way that I do that is I mirror image this thing. So I draw it again up here. So if this was, say, down here at the corner where the origin is, if I mirror that across y equals 2, I'm going to be up here at y equals 4. And then a mirror image of this endpoint would be at y equals 3, right there. And just a straight line. I'm just doing a mirror image as if y equals 2 was the mirror. And then it's going to bow out this way. Do you see what I'm doing? If I'm going to revolve this shape around y equals 2, it's going to come back up and meet up here in a mirror image of itself. So I took this point here at the origin and reflected it across here in the mirror. So if it's 2 down, then it's going to be 2 up. Do the same thing at this point. Since it was 1 down from y equals 2, the other one's 1 up. And I know that a line connected those 2 points for the inside part, so a line connected to that. And then there was this parabolic outside, parabolic outside. Okay? So draw a mirror image. And then I'm going to connect these with these ovals. Just to get a sense of the three-dimensional shape here. So again, to me it looks like it's kind of like a dome with a hole cut out, but the hole goes, back up through at a diagonal. Right, there's a hole that goes through. So the edge of this solid piece bows out and comes back to a point. But it's a circle, right, because I revolved it around that y = 2. To me, that's often the hardest part of doing this. Now what I'm going to do is I'm going to choose, okay, now which direction does this thing go? This thing goes along the x-axis, so my cross-sections need to be for a given x. Right, I'm not going to pick a value on the y-axis like I did before. Up on this one, I picked a value on the y-axis and looked at the cross-section. Since my curve is revolving around a horizontal axis, I pick something on the horizontal, like an x right there. And now I'm going to slice through at that x and look at the cross-section. Can you see it in your head? The cross-section is again a washer. There's the outside. There's the inside. I'll even color it in a little bit here so you can see it. Okay. It's not a great drawing, but if you sit back a good couple feet from your monitor and squint, it looks like the washer that I'm going for. Okay, so the cross section, what's the outer radius? Now, this is where it gets tricky. Okay, the outer radius is using the x squared function, but on this graph, x squared is this height right there. What do I actually need to measure? I need to measure from the center of the washer to the outside of the washer. That is, I need to measure from here all the way down to this curve here.
2 minus x squared.
Yep, that's exactly what it's going to be. I'm going to do that one more time so you can see it. I'm going to go from this point in black all the way down to that curve. So how far is that distance right there? It's the distance from the point of revolution to the curve now. Instead of x squared being at the bottom, it's 2 minus the x squared. Can you see that?
So that's the outer radius.
Since I'm going all the way down to this point right here, that's going to be the outer, right? Because it goes to the longest part. And I'm going to the x squared. The inner is going to be just like it, except instead of subtracting x squared, I'll subtract x. Okay? So the outer radius in this picture is 2 minus x squared, and the inner radius 2 minus x. It's from the center out to that curve when we're revolving around something other than the axis. So in most cases, I mean, I'm going to only have you revolve this about either an axis or about another line. So there's really only two options. Either the outer radius and the inner radius is going to be the functions themselves, or the outer radius and the inner radius are going to be some number minus the function. And that number is where you start. Okay? But you draw the picture, you can look graphically to be able to see where that distance is. Okay, so now the area with respect to x is what?
5 times 2 minus x squared minus 5 times 2 minus x squared.
Pi times the outer radius squared, which is 2 minus x squared, quantity squared, minus pi times the inner radius squared. Exactly. So, I'm actually going to simplify this before I integrate it. So let's multiply out those squares and collect like terms. In fact, I'm going to be even lazier. I'm going to pull the pi all the way outside and just leave him be. Factor that out. Now, what's 2 minus x squared squared?
4 minus x. Oh, no, can't do that.
Every time you forget to FOIL, a kitten dies.
Okay. That's so like 4 minus 2x.
The dog's tail falls off.
Minus 2x squared plus
4 minus 4x.
4 minus 4x squared plus x to the 4th. Yes? Okay.
minus 6.
Yes, and then I took the next step of combining the x squared. So now I have 4 minus 4x squared plus 4x to the 4th. No, just x to the 4th. There we go. And then I pulled the pi out. So now I've got, what's that? 2 minus x times 2 minus x.
4 minus 4x minus x plus x.
Right. And then if I put a minus out front, because I'm subtracting, it's minus plus minus, right? So minus 4. Oh, yeah, x
Should be just 4x.
here and x squared there. Sorry. Tablet's messing with my head here. Is that good? So minus 4 plus 4x minus x squared becomes pi times x to the 4th, and then minus 5x squared plus 4x, and that's it, right? Because 4 minus 4 cancels. Algebra. All right, so double check that. Make sure you see where I got everything. Again, what I did was I factored out the pi. So now I've just got to expand to this, which I did up top. 2 minus x squared squared. FOIL, you get 4 minus 4x squared plus x to the 4th. 4 minus 4 squared plus x to the 4th. Then I got that pi, so I multiplied out 2 minus x quantity squared, which gave me 4 minus 4x plus x squared, and then when you bring in the minus, you distribute it, you get minus 4 plus 4x minus x squared. So start with the x to the highest degree term, x to the 4th. Then the next highest of the square, so I got a minus 4 and a minus, gives me minus 5x squared. And then I've got just the plus 4x, no other x's, and then this positive 4 and this minus 4 cancel. Now we integrate. So the volume would be the integral of pi times x to the 4th minus 5x squared plus 4x. And what are all the possible values for the x? This can range from 0 to 1. Pi, and then pi just hangs out, it's a constant. Integral of x to the 4th.
X to the 5 minus 5x to the 3
Plus 2x squared.
That's,
Yeah.
when
Yes.
it's, when it's going 0 to 1 before the is it supposed to be 0 to 2? Or is it 0 to 1?
Okay, 0 to 1 is, remember I chose this x, I pick an x right here, and then draw where that cross section is. So what all possible values of x can I choose for a cross section? Notice the curve starts at x equals 0 and only goes to x equals 1. So because I'm doing my cross sections by picking this value and slicing it this way, it's how far does x move? If I went to 2, there'd have to be more curve or volume going on out here. Okay? So the range or limits have to do with where you're slicing. And your radius has to do with how high the curves are this way. Okay? I know you range over this, but you're integrating over where you're slicing, not over your radius. And that's consistent with what we did before. If I scroll up, notice on this one, I sliced here vertically and looked at the radius, and I integrated then over all possible places to slice. I didn't integrate this way, I integrated this way. And that was the same thing up here on this one. Even on the other direction, I sliced this way. I didn't integrate over 0 to 6. I integrated from where are my possible slices going. Zero to 1, which will give me pi times 1/5 minus 1/3 plus 2 minus 0, because 0 in all those gives me 0. So this is 3/15,
Minus 5.
5/15,
Negative 2/15.
plus 30/15. 2 over 1.
So 32/15.
3 minus 5 is negative 2.
Oh, yeah, 28/15.
28
Pi.
pi over 15. I don't know why it doesn't seem familiar. Did I mess up? Surely not. I wouldn't make a mistake in class.
You get 1/3. Oh, it's 5/3.
5/3. I lost my 5. That's why that number didn't sound familiar. Okay, so right here, this should be 5/3, right? So that's 15.
5/15.
So, what is that, 8/15 now? 30 minus 15.
No, it should be 25/15. It's 3 times 5 and 5 times 5. So it'll be 3/15. It'll be
25
3
here.
15ths minus 25.
I'm going to clean this up a little bit here. Because I can
So it'll
erase.
be negative 2
1,
15ths plus 30.
5/3. So this would be, how many 15ths? This is 3 minus
15ths
25 15ths plus 30. So I just get 8. Boom, chakalaka. Now, by all means, there's actually no restriction on you doing this. You have to show your work on your homework. Well, you have to show your work on your homework. You should be doing the work on your homework because you're going to have to show the work on the test. But if you get to this point right there, you've done what I'm teaching you to do in Cal 2. Getting that integral is the Cal 2 thing that you've learned. Okay? If you can get from the example down to there. Now, the rest after that is how well do you know Cal 1. At that point, you can go to your Wolfram Alpha and double check your integral. Make sure you get the right answer from here to here, right? What I care most about in here is can you set up this integral? Now, you still need to be able to do integration, so you're still going to get this wrong if you get the wrong answer along the way, but getting here is half credit. It's really the most important part of that, okay? So just getting a wrong answer here doesn't make the whole thing wrong. You got to be able to set up those integrals. Okay, let's do another one. Actually, I'm going to skip this one because it's actually the same. I'll record a video of me working this one out for you, and if you want to go back and fill in the notes, you can do that. I want to look at one other type of example. So what we've done so far in all of these is what the vast majority of your homework for 6.2 is going to be, which is take a bunch of curves and revolve them around different axes and find their volumes. Okay? So revolve volumes of solids of revolution. Now the concept of finding a volume is not just limited to revolution type volumes. There are other types of shapes that we can use this same method to find the volume for. And here's an example. This particular shape that I've got on the next page is a volume with the following property. You start with, I don't want to draw on the board because I want this on the video. Start with a circle in the XY plane. And then what I'm going to do is I'm going to draw a series of vertical lines. Boom, 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 boom. And this is just a sampling. What this is I've picked some cross sections vertically. Maybe that's the wrong word. I've picked some slices. And from each of those slices, what I'm going to do is I'm going to now create a three-dimensional figure by coming out at me. And at every one of those, I'm going to draw a square towards me. Okay? So I'm going to turn this horizontally, and you don't have to necessarily draw this. I just want you to visualize what's going on here. Let me grab my red. I'm now going to be drawing things in 3 dimensions. So let's say that circle started down here. And my first blue line was this guy right here. Okay? What I want to do is I want to use that as a side to form a square. Now, a square has to have all the same side, same length side. So I'm going to go up that same height and go back this same direction and this same height down. Okay? I just drew a square. And then at the next slice, I would do the same thing. Go up straight, go back at that distance. If I keep doing this, and then I connect all of my corners, the volume I end up with is a shape that looks like that. Notice that's exactly what I have here, is a circle on its base, and I've done a series of slices and gone up with squares all the way up, and then just connected those around. So this new shape, this volume, has the property that it is a cross-section square, right, at every width of the circle. Okay? Now, the beauty of this is that means I can find the volume of it. If I'm going to draw my little axes right here on this guy instead. Boom. Boom. There's the base. I can find the volume of it because I've got a cross-section that I can find a formula for the area. So let's say this is my x-axis right here, going back into the... Do I want to do that? Yes, x-axis. No, I want to make that my y-axis. Just follow my logic here. This is my x-axis, and this is going to be my y-axis. Okay, so here's my circle right there. All right. So what I want to do is I want to pick a value on my... No, I actually had it the way I wanted it the first time. Sorry. I want this to be my x-axis, this to be my y-axis. So I want to pick some value on my x-axis. Okay? I'm going to let that be x. Okay, so at that value of x, I'm going to look at a cross-section of this piece. Oh, I didn't go high enough, sorry. There's that square right there. Okay, so the question is, what's the area of that square? Because if I can find the area of that square, then the integral is going to go from however far forward I am here to ever how far back I am there of that area of x dx. So if I can figure out what the area of that square is, all I've got to do is plug that in right there. Okay? And it's actually, because it's a square, they're the same. So it's whatever that length is times itself. So it's something squared, right? It's the side squared. Now the question is, how long is that side? Okay? Now, come back to how I formed it. Come back up to this picture that I drew right there. Pick an x anywhere. Okay? There's my x. How long is this piece? Because that piece is the length of the side. Right? So what's the equation for the red circle? Because if I can find the equation for the top part and the equation for the bottom part, I can just subtract the two, and that will give me the length of x, right? Whatever the top half of the curve is, whatever that function is, minus whatever the bottom half. Now you remember the equation for a circle, right? And we're talking about a circle with radius r, so we have x squared plus y squared equals r squared. So solve that for y, what do you get? Which is actually two curves. It's square root of r squared minus x squared, and the negative square root of r squared minus x squared. So the top half of this curve is square root of r squared minus x squared, and the bottom half of that curve is negative square root of r squared minus x squared. Right? So how long is that side? How long is that blue line at x? It's the top curve minus the bottom curve. Plus square root of r squared minus x squared. Why plus? Minus a minus makes it a plus. So you actually get 2 inside square root of r squared minus x squared. Top curve minus bottom curve. But that's now just to get the length of the side, and then because the cross sections are squared, that's why the square is on the outside. So you actually just get 4r squared minus 4x squared. I squared the 2, I squared the square root and canceled, and then I distributed the 4. Sorry, I kept switching colors here. Switch back to blue now. Okay, so we've got the integral of 4r squared minus 4x squared. Just plugged it in, dx. Remember, r squared is a constant. It's whatever the radius of the base happens to be. It's not a variable. What is my range of all possible x's? So as I move along this x-axis here, I'll draw it. I'll point it up here on the screen. This x-axis here, I go from here all the way out to here, from here to here, right? Which comes back to this picture. Where am I allowed to move on this axis? How far over here does my x go? Negative r, right? Because it's the radius r is how far that circle extends to positive r. Okay? So again, I've done the same thing I do with my volumes of revolution. I picked an x, I cut a cross section, I found the area of the cross section in a formula, and now I'm going to range over all possible x's that I can do cross sections, okay? Which would go from how far back on the x-axis, that's this point here, negative r, to positive r. And the rest is Cal 1. For the sake of time, I will write. That. Some calculus occurs here. The final answer I get when I do that is actually 16r cubed over 3. Okay? Beautiful. All right. That's really all I have time for. This last example down here is another interesting one where I'll be honest with you about not necessarily this problem, but this problem right here. I remember vividly being in your seat taking Calculus 2 from Dr. Alms, my professor here. It wasn't in this room. In fact, it was down the hall. I graduated from here. I was in room 106, chalkboards all the way around, and we didn't have tables in there. We had those little tiny, 6-inch by 12-inch desks, and we're balancing our huge calculus textbook on one leg, a calculator in one hand, and then the notes on the desk. But this problem was in the homework in that class. The hardest problem I did through all of my calculus, to me, visually, was trying to find this volume right here. Okay? What's going on down here, a little bit different than up there, that one started with a circle, and you took these ever-increasing squares above it. This says, what happens if you take 2 cylinders, right, like cardboard paper towel roll tubes, and intersect them with each other? Okay? Or another way of thinking of it is, say you've got a machine that when you run a board through it, it turns it into a dowel, right? It turns it into a cylinder, okay? And then you take that board and you run it through one way, so you get this long tube. Now take that tube and turn it this way and run it through again, so it cuts a circle out of it. What shape do you end up with? You end up with something like this, where the 2 cylinders intersect with each other. The question is, what's the volume of this resulting shape? Okay? We have all the mathematical tools we need to be able to do it. I'm going to do it for you and not assign it as a homework assignment as Dr. Alms did for me. You'll have variations on these 2 problems in your homework. So I'm going to post these 2 videos so you can fill in the notes sometime between now and Monday, but you might want to look at those videos of how to do those 2 problems before you tackle the last couple of problems on your homework. Okay. Most of the problems on your homework, volumes of revolution, so it's outer radius, inner radius, or just radius. So those aren't as bad. These are where your cross-sectional shapes are different, right? I could change that example right above here. Instead of making them squares, I could do triangles and get a whole new type of shape. Or I could do pentagons and get a whole new type of shape. Or I could do other types of cross-sectional areas, get another volume, but the process is exactly the same. Okay, so I'm done. 6.2 homework is due on Monday. Okay.